I'll start sharing my screen. This computer is still acting a little weird, so if I go suddenly offline, that's why. Okay, it should be sharing my desktop now. So
mic
hopefully
on,
you can
mic
see
off, mic on.
the usual first screen. Okay. All right, thanks.
Mic off.
Okay, this should be the 27th, not the 22nd. Okay, so just for the record, I want to make sure that's fixed. Okay, today is the 27th. Announcements. Okay, 2 labs this week, 22 and 23. Today's lab was 22. And then Wednesdays will be 23. And last week's labs are due tonight by midnight, and those are labs 20 and 21. Survey COVID-19. Oh, that's this is screwed up. That shouldn't be there. Okay, so there's a survey on the COVID-19 shutdown that's available for 2 weeks, and the school is sending it out to everyone, like all students, and they'd really appreciate if people would give their input. So I'll let you know where that's posted, but it was made available today, and it'll be online for 2 weeks. And I'll let you know more about that in an announcement in the next day or so. Okay, the lab exam is Wednesday, May 6th, and it's just like the other exams. That is, it's posted at 8 a.m. and due by midnight, and it will cover lab calculations. And the fifth and last exam, except for the final, is next Monday, May 4th, and that will cover the last parts of Chapter 17, namely the pH and KSP parts, and also Chapter 19, which we're on now, that's coordination chemistry, and 21, which is nuclear chemistry. So there will be 2 chapters plus part of Chapter 17 on it. And there were a couple of questions today on the class project, and so I thought I'd mention this because I probably didn't make it clear earlier, but the first step of this is finding a spike protein. That is a protein that's generated by a virus, such as a flu virus or a coronavirus. And to find those, please don't search the literature because you'll really get frustrated, because not all, it's hard to tell sometimes from the title or an abstract whether it contains the information you need, and a person could read lots of articles and never really get the info that they need. But an far easier approach is to first go on Uniprot or BLAST or some other protein database and search for spike. Just enter spike in the search box. And this screenshot here shows an example of the hit list for spike. So here I just pulled up the Uniprot, and the search box is at the top. So if I enter spike with 1K, ideally, see it pulls up lots of hits here. So this would be the first step in that project. There are lots of hits, 170 some thousand. But each of these has its designated label or number. It starts with the P. There are 5 digits. Some start with other letters. And in this column over here where it says organism, it describes the origin. Like here, the top one is a human. There's avian. There are mouse. Here's equine. But anyway, we could just pick one, or we could try to narrow it down with a corona. The last time I checked, the COVID-19 wasn't in there, but it is in the Excel file. I pulled that out of a research paper that was published in, I think, February. So you already have the COVID-19 spike protein sequence. What you need to do is go on here and find one to compare it with. So here's human coronavirus, spike glycoprotein, human SARS coronavirus. You could have a look at that. And scroll down and it'll start describing the domains eventually. Yeah, here are the domains. Those are groups in this molecule that have certain tasks that they accomplish. I think you can rotate this around to have a look. It's pretty handy, and zoom in, and I think you can even choose to look at it in like a ball and stick. Let's see what this does. Oh, I didn't do anything. You can take a screenshot. Well, some of the databases have controls where you can display this in different ways. Okay, so if we go down farther, here's the sequence. So this one is 1,255 residues long. So when you find a sequence, just copy paste this whole thing into something like Word or Notepad. Just do a Control-C, Control-V, copy paste that whole thing into a text editor. And then you'll need these, you don't really need the numbers, just get the letters and then remove the blanks and string them all out end to end so there's no blanks. So you have like 1,255 continuous letters, and then that's what goes into Excel. And hopefully it'll match up to the COVID-19 sequence pretty closely. Okay. Are there any questions about the project?
Mic on.
Okay.
Mic off.
All right. Well, then let's go on to continue with chapter 19. Okay, so far in chapter 19, what we've done is nomenclature. We've learned about the different types of complexes and the IUPAC system for naming them, and we've done a bunch of examples. So now let's look further into those complexes and why they bond the way they do. And that all derives from the chemistry associated with their coordination number. The coordination number is the number of ligands attached to a central metal atom. Okay, the coordination number varies between 2 and 8. 4 and 6 are popular. And the number depends on the size of the central atom, depends on the sizes of the ligands and their charges and how they interact. And an example of complex, the coordination number 6 is cobalt hexaamine cobalt 3 ion. So there's 6 ammonias. They're all neutral, and they're the lone pair on the nitrogen is what's attaching it to the cobalt. The cobalt's a large metal atom, and it's positively charged, so it attracts the lone pair on the nitrogens, and they come in from various directions, and they're stable whenever they attach to the cobalt. So since they're neutral, the cobalt is still just as positive as it was before overall. It's just that it's more stable with the ammonias attached. So there are 6 ammonias here, so the coordination number is 6. Another example is it says tetrachloroplatinum. It looks like it has that's a 2- charge. Okay, it's a coordination number of 4. The next one's a nickel with the COs attached, also a coordination number of 4. Okay, so let's look at some common coordination numbers. And we're going to follow the PDFs that I posted on Blackboard today. This is one of them. And the other one is part of a textbook that just does a really good job of this. It's written by Kotz and Treichel. And it's called the Chemistry of Transition Elements. It's a really good book, and it does a really good job on this section. And I think it's more concise, and there are lots of useful examples in it. So it's pretty, I think it's one of the better textbooks that I've seen. Okay, so let's look at some common coordination numbers. Here's a table summarizing the various ions. The left-hand column, well, there are 2 groups. The left side and the right side are similar. They both list ion in one column and coordination number in the other. So the ion on the left starts with aluminum, then scandium, titanium, and goes all the way across the first row of D elements and continues over here all the way through zinc. Zinc's a D10 configuration when it's neutral. So from scandium to zinc, that goes across the first row. And the most common coordination number is listed for all of those elements. As you can see, most of them are 6, and there are a couple or 3 that are 4. And then copper is different from the others. The copper plus ion is only 2 or 4, whereas the divalent copper is 4 or 6. And then zinc is 4. And then the rest of these are the stable metals. They're in the D9 and D10 columns of the periodic table, like silver, gold, platinum, and palladium. So, and those have coordination numbers of usually 2 or 4. So it seems like if we look at the stable metals like copper up here, silver, gold, platinum, palladium, 2 and 4 seems to be a popular coordination number for them. And if you remember in your prior chemistry, when we predicted how molecules are formed and we predicted their shape using VSEPR theory, that was all based on sharing of valence electrons. In fact, all we needed to know to derive a VSEPR shape in a Lewis structure was to know how many valence electrons they have. And that works fine for small molecules, but for transition metals, it's a more complicated situation. And there's really no simple way to predict the shapes. We can, if you want to like go into computational chemistry and do a lot of really involved calculations, we could probably predict the shapes, but there's no like pencil and paper way like Lewis structures or VSEPR that we can derive them. So we usually have to figure them out from experimental data. So and here's a list of observations on the different coordination numbers and their structures and their electronic configurations. So for a coordination number of 2, that's the same as in VSEPR. If we have 2 atoms bonding, that has to be linear. And here are 2 examples. They're both based on silver. And silver plus happens to have a filled D subshell. And so this structure is what we would get from VSEPR. But remember, the bonding and these complexes is totally through electrons provided by the ligands. So it's not like VSEPR where the central atom has a few and then ligands have a few and they share. It's not like that at all. Here the metal atom is positive. It doesn't provide any. And the ligands come in with their lone pairs and they provide both of the electrons in each bond. So for a coordination number of 4, that structure would be tetrahedral in this case, and common examples are based on zinc or any metal ion that has a completely filled D shell, which would be a D10 configuration. Another geometry having a coordination number of 4 is square planar. And square planars are observed for complexes having a D8 configuration, such as copper, nickel, palladium, and platinum. And these are the stable or noble metals that I pointed out earlier. They're in the D9 and D10 columns of the periodic table. And then lastly is coordination number of 6, which is very popular. Lots of metals like to have coordination number of 6. That's an octahedral geometry, which is a square with 1 above and 1 below. So put together, we have 2 square-based pyramids on top of one another. And if we connect all the vertices, we get an octahedron. And with few exceptions, all the metal complexes are octahedral. And this is also true whenever we have the large ligands like ethylene, diamine, tetracetic acid, monodentate and bidentate ligands. Okay, so let's look at here the Hudson Trickle book. Here he talks about structures. Here are some models showing what I was mentioning. Here at the top right is silver with 2 ammonias attached. That's linear. See the silver in the center, and the nitrogens are the large blue spheres, and then the 3 hydrogens on each are protruding out backwards away from the center. The next one is this is square planar. And this is platinum with 2 ammonias and 2 chlorides. The next one's tetrahedral. And the last one's the octahedral. And like I said, we have the four, like the square planar arrangement in the center and one ligand above and one below. And if we connect all the red spheres with lines, we get an octahedron. Okay, so let's look at what's known as isomers. And there's some discussion of this in Jesperson, section 21.4, and also in the other handout I just mentioned. And here they talk about isomerism also. But I summarized it in these notes. Here, there are basically two classes of isomers. You have structural and stereo. Yes. And each of those classes is subdivided into two groups. So let's look at structural isomers. It has two subgroups. One's coordination and the other's linkage. And a coordination isomer occurs when the compound differs by the exchange of a coordinated ligand for a non-coordinated ligand. And by that, we mean if we look at what's inside the brackets here, everything inside of the brackets would be considered coordinated. It's an attached, in this case, an attached sulfate and 5 attached ammonias to the chromium. So that would be the complex. It's a complex ion, and the bromine that's outside the braces would be considered non-coordinated. In other words, a free counter ion. It's just basically in solution, and it happens upon this complex with a +1 charge, and it attaches to it, just like chloride would attach to sodium. So it hasn't reacted. It's not like a stable bond. It's just a counter ion. So a coordination isomer involves swapping the non-coordinated for a coordinated. So in this case, we could swap the bromine for the sulfate. So if we did that, we'd have the bromine on the inside of the braces where it's attached to the chromium, and then the sulfate would be the counter ion, which would be outside the complex, like outside the coordination sphere, just electrostatically stuck to the ion. So that these two are examples of coordination isomers, and they have different physical properties. In fact, often they're even different colors in solution. The second type of structural isomer. The second type is linkage isomers. And a linkage isomer occurs whenever we have a multi-atom ligand, such as thiocyanate and nitrite. Those are the two most common ones, and those happen to have lone pairs on different atoms. Like in the case of thiocyanate, we could have bonding through the sulfur or the nitrogen. And if the sulfur were attached to the metal, then we would call that isomer an S-bonded thiocyanate. And if bonding occurred at the nitrogen, then we call it an N-bonded thiocyanate. And similarly for nitrite, we have lone pairs on either the oxygen or the nitrogen. So we have different names to describe which isomer we have. If the oxygen's attached, we call it O-nitrito. And if the N's attached, we call it N-nitrito. Now, stereoisomers are a lot different. And those are also divided into two subclasses. The first is geometric isomers. And geometric isomers are easy to spot. The most simple of those is a cis-trans isomerism. And an example is shown here with platinum in the center and attached to two ammonias and two chlorines. And see, the ammonias happen to be next to one another, separated by 90 degrees. And the other possibility is that the ammonia could have been directly across on the other side of the platinum, like on the right-hand side drawing. Here we have the ammonias on opposite sides of the central atom. And similarly for the chlorides, they're on opposite sides. So to distinguish these two cases, we call one cis and the other trans. So the name of the complex on the left would be cis diamine dichloroplatinum 2. And on the right, it would be trans, followed by the same name. So cis and trans are used to distinguish whenever ligands happen to be as close together as they can be or as far apart as they can be. Here's another example. In this case, it's an octahedral complex. See, we have on the left chromium with, looks like 4 waters and 2 chlorines. And on the right, we have the same thing, except they're organized differently. It looks like we swap out these two, like here, we're swapping the chlorine in front for the water in front. So in the first case, see, it looks like we have waters here. These two waters are in a trans configuration. So are these two chlorines. But after the swap, we switch the H2O for this chlorine in front. We end up with a water here and a water here in a trans configuration. And similarly, we have a chlorine here and a chlorine there in a trans configuration. So we distinguish these two, like before, with cis and trans. And there is another type of geometric isomer, and it occurs in octahedral complexes. And an example here is shown. We have a chromium attached to 3 ammonias and 3 chlorides. So the 3 ammonias are shown with the blue central nitrogen there. So notice that this ammonia and this one and this one happen to share a face of the octahedron. In fact, we could draw a line that connects them and it would be an equilateral triangle. Whereas on the right, we don't have that situation. Every equilateral triangle we could draw would have, looks like 2 of one kind and 1 of the other. The 3 ammonias are connected by an edge instead. It's not a face, it's actually an edge or a meridian. So to tell these two apart, we call one the face isomer, FAC, and the other the meridian isomer, or MER. So the definitions are FAC for face and then MER for meridian. And we have another class of stereoisomer, which is called an optical isomer, or a chirality or handedness. are terms used to refer to it. These are harder to spot. And the most common examples of chirality occur in octahedral complexes that contain 2 or 3 bidentate ligands. And that would be the ethylene diamine. And here's an example of cobalt with 2 chlorines and 2 ethylene diamines. And we notice that these molecules have identical composition. It's just that they have different symmetry properties, and that gives them different physical properties, especially with how they interact with light. And that's one of the reasons they're called optical isomers. And whenever we have 2 of these types of isomers, we call them enantiomers. And we call the central atom the chiral central atom. And normally when these are synthesized, it occurs in a mixture where we have both enantiomers. And it's called the racemic mixture. And they can be separated, and they have different properties, especially with how they rotate plane polarized light. So we assign a chirality or an optical isomer based on whether a molecule can be superimposed with its mirror image. And there are some examples of this in Koch and Schreikel book here. These happen to be cis-trans isomers. Here's face and mer. Here's optical. Yeah, here are some examples of chiral molecules. If we check here on the left, if we compare this one, which is cobalt with 3 ethylene diamines, and both on the right, it's the same molecule. And if we imagine a mirror right down the middle and a vertical mirror like right here, let's say that's a mirror, and we're reflecting that molecule through the mirror. And so we transform the molecule on the left into the one on the right. So after we do so, the question is, are they equivalent? In other words, can we rotate or move these structures in such a way that they're superimposable? If they are superimposable, then that means they'd be the same structure, same geometry. But in this case, they're not. So if we imagine if we could try to make the molecule on the right look like the one on the left. So we take this molecule on the right and rotate it, say do a 180, and that would put this part here in the same location as on the left. So we rotate the molecule on the right by 180, and that makes this part here stick out to the left. So it looks like that molecule. And if we did that, the other parts wouldn't line up. And the reason is that we have the different ligands aren't independent. They're actually attached by a bridge because it's a bidentate ligand. We have a bidentate here and here, and then over here. So see, it's like a bridge that connects them. So these are tailor-made for being stereoisomers, because it's hard to get the mirror image to match up. And the same situation occurs over here. This one's contains 2 ethylene diamines and 2 chlorides. And if we have a mirror plane right between them, like right here, and do the same sort of operation, like reflect and then try to rotate one into the other, we'd see the same result, that they don't match up. Let's see, and that's about it for stereoisomers, although I should point out this, see this example 22.4, this would be pretty helpful, I think, to read over and work out because not many textbooks have such thorough examples on this. But anyway, there's like almost a full page with solutions shown in detail on how to assign isomers. Okay, so let's see. Let's go back to the PowerPoint. Let's see. Let's just go over that a little more, just cursorily. Here are the structures. We have a coordination number of 2, which is linear. 6 is octahedral. And for a coordination number of 4, we can be either tetrahedral, like this, or we could be square planar, like that. Okay, so what is the coordination number of cobalt in this complex ion? It's cobalt with 2 chlorines and 2 ethylene diamines with an overall charge of +1. Does anyone have input on that?
Mic on.
How about Maddie? Are you out there?
Yeah, I'm here, but I'm kind of lost.
Okay. On the coordination number or the whole thing?
The whole thing.
Oh, okay. It depends. No, it's not. But first, let's look at En. Is that a monodentate or bidentate? We looked at pictures of it in octahedrons with the optical isomers. And remember, they form bridges from one vertice to another. See, En is bidentate. So each En is attaching to 2 sites on the cobalt. So the cobalt is attached to 2 chlorines. Each chlorine is monodentate, and then it's attached to 2 ENs, each of which occupies 2 sites. So we have 4 sites altogether for En, and then 2 for the chlorines, which is 6 total. Yeah, so the coordination number is 6. Okay, let's go over a little bit, just kind of review a little on the isomers. Okay, so
Mic off.
let's look at chromium, 3 chlorines, and 6 waters. So actually there are 3 different isomers of that compound, and each has its own characteristic color and distinct properties. And it's because of the chlorines and the waters occupying different sites. So The first one is chromium coordinated to 6 waters, and all chlorines are counterions. That's purple. And the color is like a measure of its electronic properties. That tells us a lot about how it's bonded together inside the complex. So the other isomer would be if we swap out a chlorine for a water. So now inside the coordination sphere, we have 5 waters instead of 6. And then we have the chlorine. And now we only have 2 chlorines and a water as the counterion. And that happens to be blue-green. There are 3, or the third one has, again, 1 fewer waters inside the coordination sphere and 1 more chlorine. So outside it only has 1 chlorine as a counterion, and it has 2 waters attached, and that's green. So see, the electronic properties of these 3 compounds are very different, even though they have, like, technically they have the same overall chemical formula. Like in the first introductory chem class, we look at this and a hydrate. We'd say, okay, it's chromium trichloride attached to 6 waters, and that'd be the end of it. But there's more to the story once we look inside the bonding and we discover these different isomers and how they can cause different properties. So let's look a little more at coordination isomers. Those were the ones, well, it was just what we looked at. Those were coordination isomers. It's exchanging one inside the coordination sphere with one outside. Here's another example where we have ammonias and bromine inside the coordination sphere and sulfate outside. And then that's violet. And if we swap out a bromine for a sulfate, we get red. And we can test these easily by, is this just as if we were using any other salt? Like we could add something to precipitate out the free bromide or the free sulfate. Like we could add in the to the first one, we could add a barium chloride, which is soluble. And if the sulfate's free, then it would attach to the barium and make barium sulfate solid. So those precipitation tests can distinguish between the two. And then stereoisomers, we looked at, those were the ones that, let's see, geometric or the optical. And geometric was cis and trans. We looked at some models of that in the Koch and Treichel book. This is an example of trans because the ammonias are as far apart as possible in the top diagram and also the bottom. And then the cis isomer is where the ammonias would be closer together, like separated by only 90 degrees instead of 180. So this would be a cis isomer. Here are examples in the octahedral geometry. Here's a trans isomer. For instance, the waters are all directly across from one another, separated by the central atom. Same goes for chlorine. That's a trans isomer. And the cis isomer would occur if we'd swap out a chlorine for one of the waters. For example, well, in this picture here, they swapped out a chlorine for a water and then rotated it a little bit. But you can see that it's cis. The chlorines are 90 degrees apart. And these 2 waters are 90 degrees apart, but the 2 waters on top are still in a trans configuration. But overall, we would call this a cis isomer. And then here's an example with a bidentate ligand like the EN or ethylene diamine, showing how it attaches to one bonding site and then the other, and it creates a bridge to them. So this is what gives rise to the optical isomerism. It's because these bridges, which are created, are not superimposable on their mirror images at times. So this would be a trans configuration. And over here we have a cis, because we moved the chlorines closer together. Like over on the left, the NH2s and the bridges are opposite the central atom, as are the chlorines, whereas on the right, it's not that way. It looks like everything's in a cis configuration, except for the top and bottom NH2 groups. Okay. Let's look at which of these following complexes can have cis and trans isomers.
Mic on.
I'll just display the answer here. You can, I'll post this PowerPoint in a silent video format, so you can scroll through it and have a look and try working out some of these examples. So what we would look at here is first the overall geometry. Like here we have iron attached to 6 waters. So this would be octahedral. The next one's copper with 4 chlorines, which is either tetrahedral or square planar. And we use the rule whether it's a D8 or D10 to figure out whether it's square planar or tetrahedral. And anyway, like for D, it's manganese with 4 ammonias and 2 chlorides. That's 6 total ligands, so it's octahedral. And this is like some of the models that we just looked at. See, like this one. This is octahedral and it has 4 identical ligands and then 2 others which are alike. So it has a set of 4 and a set of 2. And if we go down here, this has a set of 4 and a set of 2. So it would be cis and trans for the same reason as the prior example. Okay, chirality, we've pretty much gone over that. That's explained pretty well in the Koch and Treichel book. Okay, so let's go to back up here. This is the class notes. Guidelines for finding isomers. These are pretty handy. So there's 5 steps. The first is to determine the number of ligands attached to the metal and determine whether the ligands are monodentate or bidentate. And knowing how many donor atoms are coordinated to the metal will allow you to establish the metal geometry. And that's the steps we were or the first step we were using in this PowerPoint slide a minute ago. So the first step is to recognize the type of ligand, like how many sites it occupies, and then establish the geometry. And then second is apply the rule that the only possible isomer of a square planar complex is geometric, which would be cis and trans. And then tetrahedral complexes do not have isomers. That makes it easy. And then step 4 is if for 6 coordinate metals, that is octahedral, they can be either cis or trans. And also we can have mer and far isomers if the stoichiometry is this Ma3B3, which means we have 3 like ligands and another set of 3 like ligands. So the FAC, that's a typo. It should be FAC, not FAR. But a face isomer would be when there are 3 A ligands all on one face of the octahedron, and the same for B. And a mer would be whenever they're, instead of being on a face, they're connected by an edge of the octahedron or along the meridian. And then lastly, step 5, the optical activity arises for complexes which involve bidentate ligands. And in these cases, drawing pictures of the molecules is pretty helpful. We would reflect them and then try to rotate the reflected molecule back into the original. And if they don't match up, then it is a chiral molecule, which is an optically active molecule. Okay, let's look at this first example. Let's draw all possible geometric isomers of these complexes. And let's go back here. Okay, here it is. Okay, here's that example. Let's start with A, iron attached to 4 ammonias and 2 chlorides. Any idea of what geometry that would be?
Mic on.
How about Brennan? Right, yeah, there are 6 ligands, so yes, octahedral. So let's draw that. This would be the first one. Okay, now how can we get an isomer from this? Okay. Okay, that's good. Yeah, so we'd end up with this. Okay, now which is cis and which is trans? It's close. That's the other way. Right, trans is when they're across, like transatlantic, like far away. Over here, trans was there. And then cis, I'm not sure what cis means in Latin. Maybe it means adjacent or next to or close to. But anyway, the right-hand one is cis. Okay. Let's go on. The other 3 can try for practice. The answers are on the last page or 2 of these notes.
Mic off.
And then here's an example with chirality, optically active stereoisomers. And if you have questions on that, we can work those next time. But these involve drawing a molecule and applying the rules, the guidelines here for optically active materials. First, check whether they're bidentate, and then whether one is cis, and then apply those rules here. Here's a third example. This is a coordination isomer. Let's look at that. Okay, here's the same example. So we have cobalt with 5 ammonias and 1 sulfate and a bromine. And we have 2 forms of it, say 1 red, 1 violet. Solutions of the red compound form a precipitate of AgBr whenever silver nitrate's added, but nothing whenever barium chloride's added. Okay, so let's write a chemical equation for this. We have the red form, which in this equation is just called red to save typing. red is actually the cobalt ammonia sulfate, and so on. So we're adding silver nitrate to it. Both of these are soluble, and then it yields silver bromide solid. And we don't really care what other stuff it yields. All we really care about is that it produces a precipitate. Okay, so because it produced a precipitate, we know that the bromide was a free ion. In other words, it was not attached inside the coordination spheres to the cobalt. It was just a counter ion, and then the silver plus easily attached to it and formed the solid. And the other observation for the red form was that when barium chloride was added, no reaction occurred. So if we put this information together, we can write the chemical formula for this. We know the bromide has to be outside the brackets because it was free. It couldn't have been inside the brackets because then the silver couldn't have taken it away from the cobalt. But so we know bromide's outside and sulfate is in, so we're all the ammonias. So this would be the chemical formula. Okay, how about the name? What's the correct name for this? How about Elizabeth? Are you out there? How about Catherine?
I'm here, but I have no idea what the correct name for that is.
Okay. How about Maddie?
Mic on.
Is Maddie out there? Okay, well, we're naming this compound. This was the fun stuff we did last time. Yeah, well, we have the rules of nomenclature we applied. If you're rusty on that, check the last PowerPoint that was posted for this. The PowerPoint video goes through 5 examples. Plus, there are rules in the notes. So the name would be pentaamine sulfato cobalt 3 bromide. And we put the amine with 2 M's first because alphabetically it comes before sulfate. And then oh, there's a typo. That should be SU, not SO. But anyway, I'll fix that. So now let's look at the other observation. For the violet compound, just the reverse occurs. So the reverse would be if we added silver nitrate, no reaction. If we added barium chloride, then we would get a sulfate precipitate. That tells us that the sulfate is free, meaning it's outside the coordination sphere. So this is a chemical formula for the violet compound. And its name would be obtained by basically swapping out the bromine for the sulfate and the first name. And we get pentamine bromo cobalt 3 sulfate. Okay. Let's go back up here. Now that brings us to crystal field splitting and magnetic properties of complexes. And that's described pretty thoroughly in this coke and tricycle chapter. And what we do is we look at the d orbitals of the metal atom. And here are d orbitals. We have 5 of them, and some of them look sort of like combined p orbitals. Like this one, actually, these 4 of the
Mic
5
off.
look like doubled up p orbitals. The weird one is a DZ squared, which has like a tire around it, like a dumbbell stuck through a tire or something, and it's pointing upward. And anyway, each of these orbitals has lobes, and there are electrons that live in these lobes. And each color lobe, or pair of dumbbell lobes, like blue here, 2 lobes, there are 2 electrons in there and 2 in the other. So altogether, we get 10 electrons can live in these orbitals, and they have directional properties. And in a free metal that is like in a gas phase where it's not interacting with anything, these orbitals tend to have shapes like this. But whenever ligands are brought close to them where they can react, they react differently because they're pointing in different directions. And these d orbitals end up splitting into 2 groups. Like before, all 5 had the same energy, but what we have is a crystal field splitting, and we get 2 groups. We have 3 orbitals in one group and 2 in the other. And for an octahedral complex, the 2 which are higher in energy are the dx squared minus y squared and the dz squared. That's the first one here, and then second one. Those 2 have a higher energy whenever ligands are brought up, higher than the other 3. So they form this split, which is known as crystal field splitting. And we use the symbol delta to measure the distance in energy from one to the other. And a similar thing happens for other geometries. For example, if we have a tetrahedral complex, a similar thing happens, but the ordering is opposite. And tetrahedral crystal field, the dx squared minus y squared and dz squared are lower than the other 3. And then we have delta, which is used again to measure the splitting. And the most complicated one is square planar, where we get 4 groups. And it's all based on the symmetry of the molecule. But so we can have 4 different levels of splitting, each with their own delta value in the case of a square planar. And the splitting allows us to predict the magnetic properties and the electron configuration. And here's an example for a cobalt-3. And we need to know how to count valence electrons. Actually, this is chromium-2. So let's look at a periodic table. Chromium is here. Here's chromium. It's a D4 element. So it has those 4 electrons in its valence plus the 2 s electrons over here. It's 4s2, 3d4. And if it's an ion, it's going to lose those s electrons first. So we would end up with 4 electrons. Oops. Yeah, 4 electrons altogether. And chromium 2+ is valence. So that's where we get these 4 arrows. It has a configuration argon core, 3d4, 4s0. So we have these 4 electrons, and normally, like based on your earlier chem class, you'd use Kuhn's rule to put those in their orbitals all with parallel spins and separate orbitals. But that's not enough of the story, because we actually have an octahedral field here, and we have different levels to consider. So depending on the value of delta, that is the splitting, we could have high spin or low spin. If we have a small value of delta, that is not much splitting, or the energy levels are the same or close to the same between the group of 3 and the group of 2. If these are close enough together, then those 4 electrons can go into a high spin configuration. We'd populate the lower 3 first, and then we'd put the 4th one up here higher, because delta is small enough to allow that. So we could have a high spin configuration, or if delta is too large for that, we'd have to pair up that 4th electron with one of the first ones. And this would be called a low spin configuration. And in either case, we would have unpaired electrons. And on the right, we would have 4 unpaired electrons, and on the left is 4, and on the right is 2. So in both cases, the complex would be paramagnetic. If all electrons were paired up, it would be called diamagnetic, meaning no magnetic properties. But this would be paramagnetic, because we have 4 unpaired on the left and 2 unpaired on the right. Now, here's a diagram showing the various metal ions, like titanium. It pretty much goes all the way across the first row, from titanium, chromium, manganese, iron, all the way over to copper and zinc. And we have low spins shown down here for some of them, it's like chromium through cobalt. It shows the low spin configuration. And up here in this group, it shows the high spin. So if we compare in the center, if we compare this area, we have high spin on the top, low spin on the bottom. What we just did for chromium is in this area, like low spin has all 4 electrons in the lower 3 orbitals. So we have 2 unpaired here, and up on top we have them spread out and 4 unpaired electrons. If we go over to manganese 2+ or iron 3+, so we have 5 valence electrons to deal with. So the low spin variety has 1 unpaired in the low spin, and the top one has 5 unpaired. So this complex would be, it would have quite a lot of magnetic strength, because it has so many unpaired electrons. And if we add another electron, see, then we can go here. This is 6. So we in the case of low spin, which is a large delta, all 6 have to be paired, and this would be called a diamagnetic complex. And if delta was small, we could promote one of those, or actually spread them out as much as possible. So we move 2 up to the higher level, and we get 4 unpaired and 2 paired. So in the top, high spin is 4 unpaired electrons, and in the bottom, it's diamagnetic. It has 0 unpaired electrons. So that's a series of examples showing the trends for valence electrons and high versus low spin. And then there are examples shown here in the left margin that show similar things. Let's see, this looks like a different geometry though. In fact, here, this has 4 levels on the left, which would be, this is square planar. Let's see, NiCl4 2-. That would be on the right. That's a square planar one. Tetrahedral's on the left. It has the 4 energy levels. So we would populate the orbitals the same as before. The only difference is that the levels are in different order, or there are more of them to contend with. Okay, and here are some examples showing how to work these out at the very end. And then we have the spectrochemical series. By the way, does anyone have questions? Okay. Hopefully someone's there.
Mic on.
Okay. All right, well,
Mic off.
so we showed how ligands, just by their mere presence, can split the D energy levels and produce magnetic complexes. And there's another way to do that, which is to vary the strength of the ligand. We have what's known as a spectrochemical series, which is a set of ligands that is lone pair donors, ions or neutrals that are capable of donating a lone pair. And they are ordered in here from left to right in order of decreasing strength. So on the left, we have cyanide ion, which is the most effective at splitting the energy levels, compared to, on the right, we have iodide, which is the least effective of this group. So a complex with cyanide attached, like let's say it's octahedral, and we have 6 cyanides attached, that would have a very large value of delta. Like the energy levels would be split a lot, and we would expect that to not be magnetic because all the electrons would have to stay paired in their lower energy levels. But if instead of cyanide it was iodide, which is weak, we would have a small value of delta, and it would be easy to populate the upper level with unpaired electrons, and that would be magnetic. And these also give rise to different optical properties. And we would measure that with a spectrophotometer. And the little device you used in lab back whenever we were on campus is an example of this, where it has a little prism inside, which is rotated. So it scans through all the frequencies of light. Like here's a little diagram showing a prism and how it splits white light into the various colors. You probably remember them as Roy G. Biv from the first letters of this set of colors here. So each of those colors has its own characteristic wavelength, and they're listed on this color wheel. For instance, between 560 and 580 nanometers is yellow. Between 580 and 620 is orange. 620 and 800 is red. That's the longest wavelength or lowest energy of the visible spectrum. And yeah, here it gives the wavelengths for each color. So the idea is to scan, like electronically rotate this prism and scan through all the wavelengths through a little slit in this this little barrier, pass it through the sample and put a detector there and record it, record the absorbance. And in your device, you took that set of absorbances and then plotted it up on Logger Pro and did that for several labs in January and February. So here's an example of an absorbance curve. Here's the wavelength across the bottom in nanometers and the corresponding color at the top. And this is the absorbance of titanium with 6 waters. It's an octahedral ion. And we can see that the absorbance goes through a maximum at about 500. Okay, so let's look at this question here. They want to know from its absorbance, what color light is absorbed by the ion? And what is the color of the solution? Okay, does anyone have an idea on that?
Mic on.
How about Catherine?
What is the color? Is it blue?
Well, are you referring to the solution or the color it's absorbed?
The color that's absorbed.
Well, let's look at where the hump is. You're right, it does go up in the blue, but they really shouldn't show that. That's kind of off scale. They're talking about this hump right here. This one.
Yellow.
Right. Yeah, so what would the color of the solution be? If it absorbs yellow, we can use the color wheel. Like, what's the complement of yellow? Use this color wheel here.
Like what numbers? Or I'm confused on what you're asking.
Well, the color wheel is like if something, for instance, if something absorbs green, then it transmits everything else and makes red light. So if something absorbs green, it would give a solution that's red.
So if it's yellow, it would give me that dark, kind of dark blue.
Yeah, or purple, right. Yeah, so the color of solution would be blue, purple. And we have an example here, number 6, which is similar. Here it says it absorbs light at 700 nanometers. What color is a solution? So if we go to 700 nanometers here in this table, that would be red. So what would the color of the solution be? Right, it'd be green. And the other examples we can go over next time. But at this point, we won't really be introducing much new information. Really, it's just going over what we have here, these 2 sets of notes. We'll go through these examples and review whatever you want next time for the next exam. So the answers for all of these examples are in the last 2 pages. Scrolling through them now. So you can have a look and practice with those, and we'll go over those next time. Okay. So I'm going to shut off the recorder.